Oh, anyone is in live? Anyone is in live? Good evening, everyone. Good evening. Yes, yes. Right. Okay, fine, done. Now, in the last class, we have done up to the which one? Up to how to identify the reversible process and irreversible process, right? Now, in the reversible process is nothing but the slow process, clear? And in the irreversible process, it will be happening against the constant external pressure and it is a fast process. Here, the next very important we are going to see, and the one new thermodynamic parameter that we are going to study, that we call it as a which one? Internal energy. Clear? Now what is the meaning of the internal energy? Internal energy is nothing but, now whatever may be the heat it is exchanging. Clear? Now the internal energy, in some books they are representing by the E, or some books they are representing by the U. Okay, you should not get confused, both are same. Internal energy, E or U, both are same. Clear? Internal energy. Now what is the meaning of the internal energy? Every substance possess some energy internally. Clear? Is called internal energy. So what does it mean, internal energy? Clear? Now internal energy, E is equal to potential energy plus kinetic energy is nothing but internal energy. Every system possesses some energy internally. How? Due to the kinetic energy, due to the potential energy. Let's suppose this is our system. Okay? This is our system. Now in this system we are having some gas particles. This is our system and we are having the gas particles. Now in this our system, when it is having the gas particles, clear? Now this gas particle will move here and there, from here to here. This gas particle will move here and there. Now this gas particle will move here and there. This gas particle will move. Clear? Now when these gas particles are moving from the one place to another place, what it is happening? Now this gas particle and this gas particle will repel. Some other gas particle and this gas particle will be attract, and this gas particle and this gas particle, interatomic attraction, intermolecular repulsion. Now due to the attraction and the repulsion between the gas molecule, what it is generating? It is generating the potential energy. Clear? Now due to that potential energy, what happened? Whatever may be the energy, potential energy, due to that energy, what it will happen? Energy is releasing. Now when the energy is releasing, this system, what happens? Energy, it is increasing. Clear? What does it mean, the internal energy? Every substance possesses some energy internally. How it is possessing some energy internally? Due to this gas particle movement from the one place to another place, due to that attraction, repulsion, due to the potential energy it is getting. Clear? Next. Now through the potential energy we are getting internally. Through the kinetic energy, how we are getting? Kinetic energy, how the system is increasing the internal energy through the kinetic energy means through the translational energy. Clear? Now through the translational energy plus rotational energy. Clear? Plus vibrational energy. Now how these gas particles are having this energy, I will explain very clearly. Clear? Through the electronic energy. Now through this type of the energies, now these gas particles, it is changing kinetically through the kinetic energy, through the potential energy of these gas particles. Now that's the reason only the system is having the energy internally. Clear? I hope how the every system is getting internal energy because due to the movement of the potential energy and as well as the kinetic energy. I hope it is clear. Now the very key point of the internal energy is, now what is the key point of the internal energy and the definition of the internal energy is the heat content of the system, heat content of the system measured, heat content of the system measured at constant temperature and constant volume. Constant temperature and the constant volume, whatever may be the heat exchange it is happening, that we call it as a internal energy. Means let's suppose this is our system. Clear? Now this system, now the wall is fixed, right? Now only one thing you have to remember, if the wall is fixed, if this wall is rigid, this wall is rigid. Now if the wall is rigid, what it will happen? Volume is fixed. If the volume is fixed, whatever may be the heat exchange it is happening, whatever may be the heat exchange it is happening in the system, that it is measured at constant volume, whatever may be the heat exchanging from the system to the surrounding. Clear? Now the system to the surrounding. Hi. Now, hi Chaudhary, hi. Now whatever may be the system it is exchanging its heat at a constant volume, we call it as the internal energy. But my dear friends, you have to be very careful with the internal energy. Exact value of internal energy cannot be calculated. Why the exact value of the internal energy cannot be calculated? Because let's see, this gas is having the different potential energy. This gas is having the different kinetic energy. This gas is having the different potential energy and kinetic energy. Because exact value of internal energy at that time we cannot be calculated. But what we can calculate from the initial state to final state, if it is changed. Now from the system when it has changed from this state to this state, now the change, what may be the change in internal energy. Clear? Now the change in internal energy can be calculated. Change in internal energy can be calculated. Clear? Exact value cannot be calculated. Now, yeah, Chaudhary, may I know where are you from? And you are preparing for any JEE or NEET. Clear? Now what are the characteristics of the internal energy? Characteristics of internal energy, E or U. Clear? The exact value of internal energy cannot be calculated. First point. Exact. Okay, good. Exact value of E or U cannot be calculated. You are in the first year or second year? Clear? Now it is a extensive property. It is extensive property. Done? Next. What we can calculate? Change in internal energy can be calculated. Change in internal energy can be calculated. Change in internal energy means delta U is equal to U final minus U initial. Clear? Okay. Fine. Now you can listen to the class. Okay. Now Chaudhary, you can listen to the class. This is a what? Thermodynamics lecture it is going on. Right? These are the key points you have to remember for the internal energy. Next one. Max I will try to finish up to the first law. It is lecture wise only, not one shot type. It is lecture wise only. Now the next we are going to see, that is heat and the work. Now what is the meaning of the heat? Now the heat is nothing but when there exists difference in temperature, energy, difference in temperature, energy flows from the region of high temperature, from the region of high temperature to low temperature, to low temperature. Okay, my dear friend. Now whatever may be the compliment you are giving, thanks for it. Okay, now we know, right, heat will flow from the high temperature to the low temperature, right? Heat will flow from high temperature to the low temperature. Now the heat is a disorder form of the energy and work is the order form of the energy. Now how come the heat is a disorder form of the energy and how is the work is the order form of the energy? Now I will explain. Now let's suppose here this is one room, let us assume, right? Now in this room we are having the gas particles like this, right? Now here also one gas particles we are having, right? Now in the middle of the room, now what I will do, just I will start the heating of this room. Now this is heat. When I was heating in the middle of the room, whatever may be the gas particles, it is nearer to the heat, it will express the high heat, it will feel the high heat, right? Now when the gas particles which are far away from the heat will express the lower heat, means it is having the less heat which are far away from the heat. Now the gas particles which are nearer to the heat are that fire, it will express the higher heat, right? Means uniformly we are not getting same heat in the entire room. So that's the reason heat is a disorder form of energy. Heat is the disorder form of energy. Uniformly heat is not distributing in the entire system. Now but if you see the work, if we are having books in the random manner, let's suppose if we are having the books in the random manner, we can place everything. Clear? Orderly we can place the books, right? Now work can be done orderly. If it is in the form of disorder form also, we can make it in the order form. So work is the what we can say, work is the ordered form. Now we'll see now how the work can be done in the thermodynamics. Now we'll see. Work can be done either through the expansion or either through the compression. Now how it can be done through the expansion and through the compression, now we'll see. Here in the thermodynamics we are having the two types of the work. Now what are the two types of the work we are having? One is non-PV work, and one is a PV work. Sir, what is the meaning of the non-PV work and what is the meaning of the PV work? Means non-PV work means only one thing you have to remember. Now if work is happening, but no change in volume, if the volume is not, if work is happening but there is no change in the volume of that system, then that type of the work we call it as a non-PV work. I will explain what is the meaning of non-PV work in the upcoming lectures. Majorly we are going to see with the PV work. In the PV work, change in volume will be happen. By seeing the change in volume, we can define the work. Clear? Now, to define the work, I was explaining on the basis of the one PV curve. Clear? Now, PV curve, let's suppose, now this is the one curve I was taking. This is the pressure and here is a volume. With the example of the one movable piston I will take. This is the one movable piston we are having. This is one movable piston we are having, right? Now in this movable piston, this is the volume. Initial volume it is V1. right? Now this is some external pressure, P external pressure. By applying the external pressure on this gas, for this gas what I was did, I was applied some external pressure. When I was applied some external pressure on this gas, now this piston has been moved up to here and it has been stopped. Clear? Now this is the final volume, right? Now this is the final volume. This is V2. Clear? Now area under the PV curve will be the work done. Clear? Now whatever may be the area, this is a pressure. Now area under the PV curve, you have to be very careful how to calculate the work in the PV graph. Means area under the curve will give you the work done. Area under the PV curve is work done. Clear? Is the work done. Done. Now here you can see initially our piston or our system is having this much volume. After I was doing the work by applying the external pressure, now my system has been changed the volume up to here. Now this is the area under the PV curve, right? Now this is the area. This much work my system has been done. This much work my system has been done. You can see from V1 volume to it has reached to the V2 volume. Now you can see here from the V1 volume to V2 volume. Now the change in volume delta V. The change in volume we call it as a delta V. Change in volume delta V, what we call delta V is equal to area into length. Change in volume, this much area from here to here, this much length. Clear? Now from the V1 to V2, this much length it has been changed and this much area it has been changed, right? Clear? Now change in volume is area into length. Now by applying some external force only, now this piston has been moved up to here. By applying some external force only, the system has been moved up to here. Means external force by applying the pressure, that is force by area. Pressure is equal to force by area, right? Now if you send the area to the left hand side, now the force of the piston will be equal to the pressure into area, right? Now how much work done I was did? Work done formula, work done is equal to force into length. Force into length. Clear? Now the force formula what I was having, pressure into area into length. Clear? Now you can see here, now area into length is the change in volume. Area into length is equal to change in volume. So work done is equal to P external pressure, whatever maybe we have applied, P external into delta V. Now this is the work done formula. This is work done only. This is work done formula only. Clear? Now based on this formula, we have to see work done on the system and work done by the system. I explained very clearly work done by the system and work done on the system. Whatever may be the unit conventions we are having in the physics and the chemistry, it will be different. Clear? Now we'll see work done formula. We got it as P external into change in volume. Clear? Now the change in volume formula, what is the change in volume? Delta V is equal to V2 minus V1. Now here we are going to see the two types of the work. First one I was taken on the basis of the example of the work done on the system. See, in the first this much volume of the piston we are having. After doing the work, now my piston has been changed here. Now this is a V1 volume, let us assume 10 ml. After doing the work I was did on the gas, right? This is a gas. Gas is nothing but our system. Now when I was applied the pressure, I was compressed this piston. When I was compressed the piston, the work is done on the system, right? When the work is done on the system, now the final volume has been reached to the 5 ml. Final volume has been reached to the 5 ml. Clear? Now the change in volume from where to where? Now initially it is having the 10 ml and the finally it is having the 5 ml. Now the overall delta V value, how much I will get? I will get the negative, right? Overall, I must got it as a negative. So here the delta V value, I got it as a negative, means work done formula, work done is equal to minus P external delta V, minus P external delta V. Now this is a work done formula we are having. Clear? This is a work done formula we are having. So if you want the overall change, work done, or this is for the large change, and if you want to for the small change, work done is equal to minus P external from the V1 to V2, P external delta dV. Clear? Now this is a work done formula. Now based on this work done formula, now work done on the system, work done by the system. May I know work done by the system is negative or positive? Work done by the system is negative or positive? Work done by the system. And work done on the system. Work done by the system is negative or positive? And work done on the system. Work done by the system is positive or negative? Work done on the system is positive or negative? Work done by the system is positive. Good. Now work done on the system. Work done on the system. Work done by the system, it is negative. Work done on the system, it is positive. Sir, how sir? Now listen. Here, now work done by the system is negative. Work done on the system, it is positive. See, work done by the system, it is negative. Why? Because let's suppose this is a container. This is a container. Now this container, initially it is having the volume of V1 is equal to 10 ml. Work done by the system means system is doing the work, means this piston will be expand. Now when this system has been expand, when this piston has been expand up to here, now the final volume has become 15 ml. 15 ml, right? Now the change in volume, V2 minus V1. Final volume is 15, initial volume is 10. Now the delta V value, how much we got? Delta V value, we got it as a positive. If the delta V value, if it is getting as a positive, now you can see. If the delta V value, if you getting as a positive, W is equal to minus P external delta V. Now in the work done by the system, delta V we got it as a positive. So negative into positive, work done, what you will get? Negative you will get, right? Negative will get. Now work done on the system, just now we have seen work done on the system. Now I just compressed the piston. When I was compressed the piston, now the change in volume has been decreased. Change in volume has been decreased, it means delta V got it as a negative. If the delta V, if you are getting it as a negative, delta V if you are getting it as a negative, now the work done is equal to minus P external delta V. Negative into negative, work done you will get it as a positive. Here work done by the system is negative and work done on the system is positive. I hope it is clear. I hope it is clear for everyone. This is a very key points you have to remember. Work done by the system is negative. Work done on the system is positive. Clear? Next. Units of the energy or work. Clear? Now units of the energy or work now we'll see. Now these units are very important. So you have to be very careful with the units. Right. Okay. Now what are the units you have to remember? First, 1 joule is equal to 10 to the power 7 ergs. Clear? Next, 1 joule is equal to 1 by 4.184 calories. Right? Now 1 calorie is equal to 4.2 joules. Now these are the units you have to remember. Clear? And the next unit. This unit will play very crucial role for the work done. Most of the cases, what they will do, we know work done formula. Work done is equal to what? Minus V1 to V2 P external dV, right? Now the pressure unit we know ATM, and the volume unit we know that it is a liter. Clear? Now they will ask you one random question, they will give you, and they will ask you how much work done by the system or work done on the system. In joules they will ask, in joule level that. So work done formula, most of the cases we will use this one only, and whatever may be the data they will given in the question, P external dV, but work done unit we are getting it in the ATM and liter, but they are asking in the joule. So for that one we are having a one beautiful unit, that it is 1 ATM liter is equal to 101.2 joules. 101.2 joules. Sir, how this 101.2 joules it has came? This is very important, my dear friends. Sometimes they may or they may not give in the question. You have to be very careful. Work done, if they ask in the joules, you have to use 101.2 joules. 101.2 joules you have to use. See how this it has came. Now I will derive this one. Now we'll see. Now we know universal gas constant R values. R is equal to 0.0821 ATM liter per mole Kelvin. This unit it has came from the ideal gas equation. PV is equal to nRT. Clear? PV is equal to nRT. R is equal to PV by NT. Clear? Now at a STP condition, one volume it will be occupied 22.4 by number of moles 1 and temperature 273 Kelvin. If you do, you will get the 0.0821 that I was explained very clearly. Clear? Now this is the 1 R value. Now another R value we are having, R is equal to 8.314 joule per Kelvin mole. This is a 1 R value, 2 R values we are having. When we are equating these 2 R values, 0.0821 is equal to 0.0821 ATM liter per mole Kelvin is equal to 8.314 joule per Kelvin mole. Now Kelvin mole will be cancelled. Now if I take it 0.0821 to the left hand side, now the ATM liter is equal to 8 by 314 by 0.0821 joules. If you divide that, you will get the ATM liter is equal to 101.2 joules you will get. This will play a very crucial role. After whatever may be the data they have given in the question, after giving in the question, if you multiply with the 101.2, that it will give you the work done in the joules. Clear? Now the next one, if they are asking in the, sometimes instead of joules they will give you in the bar, or in the pressure unit they will give you in the bar also. So for that one, another 1 joule is equal to 1 by 101.2 ATM liter. Right? Next, another very important you have to remember, 1 ATM liter is equal to 24.2 calories. 24.2 calories. Now how much in joule? 1 ATM liter is equal to 101.2 joules. These two will play a very crucial role. These two units will play a very crucial role. You have to be remember. Then next, 1 liter bar is equal to 100 joules. Right? 1 joule is equal to 1 by 100 liter bar. Clear? Now these are the some units you have to remember. This will play very crucial role. Now I will write the one question. Now what is the answer for this question? Now you have to say, right? A gas expands by 0.2 liter against constant pressure of 1 atm. Calculate work done in joules and calories. Now see, in joules and calories. Send me the answer. In joules and the calories. In the joules and the calories, I need the answer. What is the answer? Are you trying? What is the answer you got? Are you trying? 20.24 joules. 20.24 joules. Okay, fine. Next in calories. .84. Okay, 20.24 in the calories we got, and 4.84 calories we got. Okay, good. Fine. Now, next, very important and the conceptual reactions I will write. Based on that one, you have to say whether the given reaction is a work done by the system or work done on the system. Okay, you will get to know by seeing the which one, by seeing the volume change in the given question. You have to cross check whether the given one is a work done by the system or work done on the system. Okay, fine. Now let's suppose here work done is equal to minus P external, volume already they have given, change in volume, it is 0.2. So minus 0.2 atm liter we got, atm liter, but atm 1 atm liter is equal to 101.2 joules and 24 point, how much we have to do, 24.2 calories. If you multiply for the given 0.2 into 101.2, it will give you the joules, and 0.2 into 24.2, it will give you in the calories, right? Next one, let's suppose one reaction they have given like this. What is the gas? Let's suppose 2 light. N2 gas plus 3H2 gas gives rise to 2NH3 gas. Now this is work done by the system or work done on the system? Now say me, this is work done by the system or work done on the system? Work done by the system or work done on the system? Work done by the system or work done on the system? Until first law reversible, irreversible, maximum, first law and the first law questions. I will finish the first law and the first law questions. Now here you will see, initially we are having the volume is directly proportional to the number of moles. By seeing the number of moles also we can see. Now here we are having the 4 moles of the volume at the reactant side. Now the product side, what it has happened, 2 moles it has happened, right? Clear? Now initially volume is 4, let us assume. After converted into the product, it has become the 2. Means volume of the system has been decreased or increased? Volume of the system has been decreased, right? If the number of moles has been decreased, means obviously the volume will be decreased. Means why come it will be work done by the system? It is work done on the system. It is not by the system, it is work done on the system, my dear friends. You have to be very careful. Clear? Here by seeing the number of moles you can say it is not work done by the system, it is work done on the system. Work done on the system. Clear? It is not work done by the system, it is work done on the system. Okay. Now let's suppose, if they have given in this manner, V is directly proportional to the N. Next one. Next, suppose if they have given in this manner, H2O is converted into H2 plus of O2 gas. Right? Now you say me, in this reaction, work done on the system or work done by the system? Work done on the system or work done by the system? Work done by the system or work done on the system? It will give you the work done by the system. Clear? Number of moles it is increasing, right? Number of moles if it is increasing, work done by the system. If the number of moles if it is decreasing, it is work done on the system. Now this is a work done, here the one, but here the number of moles is increasing. Number of moles is increasing means work done by the system. Work done by the system. Okay? Clear? Done. Right. Now the next very important of our thermodynamics, that is the first law of thermodynamics we are going to study. Now what is the meaning of the first law of the thermodynamics? The first law of the thermodynamics is saying that energy cannot be created nor be destroyed, it is saying. Clear? Now, how the first law of the thermodynamics formula it has came? Let's suppose I was taking the one system. This is one system. every system it is having some internal energy U1 we know. Let's suppose I was consider this system it is having some internal energy U1. Now I want to change this system internal energy. How I can change this system internal energy? Now I will change this system internal energy by giving the heat. By giving the heat. Now by giving the heat, what it will happen? System internal energy will be increase or decrease? My dear friends, you have to say me. Now when I was giving the heat to my system, this is my system. For my system, initially it is having internal energy U1. So I want to change my system through the heat. Through the heat I want to change the system. When I was supplying the heat to my system internal energy will be increase or decrease or remain same. My system internal energy will be increase or decrease or remain same. My system internal energy will be increase or decrease or remain same. I hope whatever may be the point I was asking, I hope it is clear for you. I hope it is clear what is the point I was asking you. Now you see, when I was giving the heat to the system, now the system is absorbing that heat and it will be changed. How my system has been changed? My system internal energy has been changed due to the supplying of the heat. Due to the supplying of the heat. Now after that, now again my system internal energy I will change by the work. Now by the work, when I was changing, if I was compressed my system, what it will happen? Now my system internal energy will be changed. Through the work I was changed, through the heat I was changed my system internal energy. Now this is the final internal energy, right? Now this is the final internal energy. Now the system initially it is having the U1 internal energy. After U1 internal energy, with the heat I was changed the internal energy. After that, with the work I was changed the internal energy. Now this is the final internal energy of my system. Now this will be equal to the final internal energy of the system. Now if I send that U1 to the left hand side, now U2 minus U1 is equal to Q plus W. Now U2 minus U1, can I write it as a change in internal energy, delta U? So by this we got the first law of thermodynamics formula. Now the first law of the thermodynamics formula, it is saying, what it is saying? Delta U is equal to Q plus W. This is the first law of thermodynamics formula. Now here the delta U is equal to U2 minus U1, final internal energy minus initial internal energy. In this manner we got the first law of thermodynamics formula. Now here the first law of thermodynamics formula will play very crucial role. Only the key points you have to remember: work done on the system is positive, work done by the system is negative, right? Next, very key point you have to remember: heat absorbed by the system, heat absorbed by the system is equal to positive. Heat evolved or heat released, heat evolved by the system, heat evolved by the system is negative. These are the key points you have to remember. If you remember these sign conventions, you will not get any mistake while you are solving the questions, right? Now by using the first law of thermodynamics, now we are, this first law of thermodynamics we are applying in the thermodynamic processes. What are the thermodynamic processes we are having? First one is the isothermal process, right? For the isothermal process, if I was applying the first law of thermodynamics, now in the isothermal process, which is constant? temperature is constant. For the isothermal process, temperature is constant, right? Done. In this, if the temperature is constant, now we know internal energy. This is a system. Okay. For the system, we are having the gases. Right. Now, every system having the internal energy due to potential energy plus kinetic energy. Right. Potential energy it is getting when they are attracting, when they are repelling. Clear? Now, kinetic energy means nothing but movement of the gas particles. Let's suppose if I made the temperature constant. Temperature constant if I made, what it will happen? This whatever may be the gas particles it is present, it will be present in the same place. It will not move here and there. Whatever may be the gas particles it is there. When there is no movement in the gas particles, there is no potential energy of it and there is no kinetic energy of it. When the movement of the gas particles, if it is not having, we are not having the potential energy and the kinetic energy. When the potential energy and the kinetic energy, if it is not present and the constant temperature, when there is no change in the internal energy, means in the isothermal process, if the temperature is constant, kinetic energy of the gas particle is constant. If the kinetic energy is constant, potential energy is constant. If the potential energy is constant, internal energy is constant. So this is a key point you have to remember. In the isothermal process, temperature is constant. If the temperature is constant, which is constant? Internal energy is constant. Internal energy is directly proportional to the temperature. Clear? Temperature is constant means U is constant. If the U is constant, we know delta U is equal to 0. We know according to FLTD, first law of thermodynamics, for the, this is large change. This is the large change. For the small change, we are having the formula du is equal to dq plus dw. du is equal to dq plus dw. This is for the small change. Now, if the internal energy du is equal to 0, then what it will happen? dq will be equal to minus dw. dq is equal to minus dw it will become. Clear? Now, in the isothermal process, dq is equal to minus dw. Now, second one. Second process we are having the adiabatic process. Second one we are having the adiabatic process. Now, my dear friends, can anyone say me in the adiabatic process which is constant? In the adiabatic process which is constant? In the adiabatic process which is constant? Can anyone say me in the adiabatic process which is constant? In the adiabatic process, heat is constant, right? In the adiabatic process, if the heat is constant, now according to the FLTD is equal to Q plus W. If Q is 0, delta U is equal to W, right? For the small change, du is equal to dw. Means by utilizing some internal energy of the system is doing the work, right? Now, according to the FLTD in the adiabatic process, du will be equal to the W. du will be equal to the W, right? Next, third one, isochoric process. In the isochoric process which is constant? In the isochoric process which is constant? In the isochoric process which is constant? The isochoric process which is constant? In the isochoric process which is constant? In the isochoric process V is constant. In the isochoric process, if the V is constant, according to the FLTD, now du is equal to dq plus dw, right? Now we know dw is equal to minus P external dV. Clear? Now here the dV is equal to change in volume will be 0. If the change in volume 0 means W is equal to 0. Clear? Now if the dW is equal to 0, du will be equal to the dq at a constant volume. Now at the constant volume, whatever may be the heat we have supplied, that is utilizing to increase the system internal energy. Clear? Done. Next, fourth one. This is a one very important, that is isobaric process. Before going to the isobaric process, I want to introduce you one new thermodynamic parameter, that is a enthalpy. One new thermodynamic parameter I want to introduce to you, that it is a enthalpy. Okay. Now what is the meaning of the enthalpy means? Why this enthalpy term it has been introduced? Enthalpy is introduced by the H. Okay. Now enthalpy, what is the meaning of the enthalpy? Let's suppose this is a system. From this system, here the rigid container we have taken. Rigid container means constant volume. Done. From the constant volume, whatever may be the heat it is coming, whatever may be the heat it is going, that measurement of the heat measured at the constant volume, clear, constant volume and the constant temperature, we call it as internal energy we have studied. Now here I don't want to put the constant volume. If I don't want to put the constant volume, what I have to make? I have to take the open vessel. If I take the open vessel, volume will not be constant. Done? Done. Here, now, which thermodynamic parameter is constant now? Constant pressure. Now it is a constant pressure. When whatever may be the heat it is exchanging and whatever may be the heat it is absorbing, the change in heat and the change in whatever may be the heat exchanging in the process, that it is measured by the new thermodynamic parameter, that it is called as a enthalpy. That it is called as a enthalpy. What is the definition of the enthalpy means? The enthalpy definition is the heat content of the system, measured at a constant temperature and the pressure is called as a enthalpy. Clear? Heat content of the system measured at constant temperature and pressure is called enthalpy. Clear? Now the enthalpy is also a one extensive property. Enthalpy is also a one extensive property. Exact value of the enthalpy cannot be calculated. Only the change in value can be calculated. It is extensive property. Extensive property. And delta H, H2 minus H1 can calculated. Now the enthalpy formula that we got, H is equal to E plus PV at constant pressure. Clear? At constant pressure. Now the enthalpy formula we got it as a E or U, anything you can give. You should not get confused. Sir, here what is the meaning of E? E is nothing but internal energy only. Clear? Now by using this enthalpy formula, now we are going to derive the isobaric process, and what we are getting, the formula. What is the formula we are getting? Now we'll see. Now here in the isobaric process, which is constant? P is constant. In the isobaric process, P is constant. If in the isobaric process the P is constant, according to the FLTD, right, we know internal energy delta U is equal to constant pressure. Now work done formula we are having P into V2 minus V1, change in volume, right here. Now internal energy formula U2 minus U1 is equal to QP minus PV2 plus PV1, can I write? Done. Now if I send this PV2 and PV1 to the left hand side, QP will be equal to U2 plus PV2 minus of U1 plus PV1. Can I write? Both it will become same, right? Minus into minus, minus U1. And if I send it to the left hand side, it will become minus, right? Minus into plus, it will become minus. Now we know, just now we have seen internal energy is equal to U plus PV. Right? Here if you are getting confusion, you can write U plus PV also. H is equal to U plus PV. Done? Now, here the QP will be equal to the H2 minus H1. H2 minus H1 is nothing but QP will be equal to the delta H. Now, whatever may be the volume we have changed, or whatever may be the heat we are passing at the constant pressure, that it is utilizing to change its system enthalpy. System enthalpy. Clear? Next. Next we are going to see one very important term that we are going to see, that is a molar heat capacity. In the starting we have seen, right, heat capacity. Now we are going to see the molar heat capacity. Now, molar heat capacity, one, you have to be very careful, my dear friends. If you see the term molar, molar means intensive property, fixed. Molar means fixed. What is the meaning of the molar heat capacity? The heat required to raise the temperature of 1 mole of substance. 1 mole is fixed, right? 1 mole of substance through 1 degree. Through 1 degree is known as a molar heat capacity. This molar heat capacity, let's suppose, listen. If I take the 100 moles of the substance, I require 100 kilojoules of energy. If I take the 50 moles of the substance, I require 50 kilojoules of energy. Then now for the 100 moles 100 kilojoules, for the 50 moles 50 kilojoules, means from this one, from the 100 moles I will take only 1 mole. From this 50 moles I will take 1 mole. Then both the cases I require the heat, it is 10 kilojoules only. Means 100 moles you take, 50 moles you take. In that 100 mole, if you take it 1 mole and if you calculate, that heat is fixed. For the 50 mole, if you take the 1 mole and if you cross check the heat, that heat it is fixed. All the fixed properties of the heat is called as the, which one? Intensive property or extensive property? Intensive property. Clear? Now, here molar heat capacities are of the two types. Molar heat capacities are two types. One is CV and one it is a CP. What is the meaning of CV and what is the meaning of CP? Means molar heat capacity at a constant volume. This is CP, means molar heat capacity at a constant pressure. Right? Now CV is equal to heat capacity by number of moles. Heat capacity formula Q by delta T. Right? Now CP is equal to heat capacity by number of moles into delta T. Now here CV at a constant volume, heat supplied will be equal to the change in volume. Now at a constant volume, at a constant pressure, change in volume will be equal to the delta H. Now CV is equal to delta U by NC N delta T. CP is equal to delta H by N delta T. Right? Now these are the two formulas we have got for the CP and the CV. Now CV is equal to delta U N delta T. Cp is equal to delta H N delta T. Then if you take it to the left hand side, delta U is equal to NCV delta T. Now delta H is equal to NCP delta T. Clear? Now these are the formulas, we got it. Done. This is the one key formulas we have to remember. These are the some key formulas we have to remember. Right? Now we'll see the what is the relationship between delta relation between Cp and Cv. Now at constant pressure we know H is equal to U plus Pv, enthalpy formula. Now for 1 mole of gas, Pv is equal to RT we know. Then H is equal to U plus RT. Now the entire equation I was differentiating with respect to T. If I was differentiating with respect to the T, then entire equation will become dH by dt is equal to du by dt. Tt get cancelled and it will become R. Now we know dH by dt will be the Cp, du by dt will be the Cv. How, sir? Now you see. Here this is for the large change. For the small change I can write like this, right? du by dt for 1 mole, this will become 1. Now this one I can write it as a Cp is equal to dH by dt. Done? Now here also then can I write it as a Cp is equal to Cv plus R. Then if you send the Cv to the left hand side, now if I send the Cv to the left hand side, then it will become Cp minus Cv is equal to R. This is for the 1 mole. Done? Clear? I hope it is clear. Now the next we are having Poisson's ratio. Poisson's ratio. Now what is the meaning of the Poisson's ratio? Means Poisson's ratio gamma. Now gamma is equal to Cp by Cv. So how to calculate this Poisson's ratio? Clear? Now how to calculate the Poisson's ratio? That on the basis of the which one? Equipartition energy. Now what is the meaning of the equipartition energy or degree of freedom? Clear? Right. Now equipartition energy. Right. Equipartition energy or degree of freedom. My dear friends, now this is a entirely purely of your physics topic. In your physics also you will get, but I will explain very clearly. Now listen. Degree of the freedom. What is the meaning of the degree of the freedom? What is the definition of the degree of the freedom? Means the number of independent ways through which a system can exchange energy. Clear? Now there are 3 types of the degree of freedom we are having. First one, translational. Second one, rotational. Third one, vibrational. third one vibrational. 3 degrees of the freedom we are having. But in the normal temperature, vibrational we will not consider. Okay, for the normal temperature, at the high temperature only we'll consider. What is the meaning of the translational? Means the number of independent ways through which a system can exchange the energy. The number of system can exchange its energy. Now first one I will go through the monoatomic gas. I will go. Okay, for the monoatomic gas, if I want to calculate the monoatomic gas for the degree of freedom, monoatomic gas, for the monoatomic gas for the degree of freedom, if I want to calculate, Cv is equal to E by 2 R and Cp is equal to Cv plus R. This is the formulas we are having. How to calculate the E? Means E is equal to translational energy, E or F, both are same. Okay, don't get confused. E or F. Now translational plus rotational. Okay, rotational. Now vibrational we will not consider, right? Translational means if I was taking the axis like this, this is the one monoatomic gas. Example, helium or anything I will take. Monoatomic gas, it can translate. What is the degree of freedom formula definition? The number of independent ways through which a system can exchange its energy. Now if suppose this gas is translating in between these two, it is translating in between the x and y only. It is translating in between the x and y, but now it is depending on the which one? It is depending on the 3 axis, right? In the 3 axis it is translating. It is x, it is y. Now if I keep the axis z in this manner, on the 3 axis it is translating. So for the every gas, translational degree of freedom will be 3. Now rotation means, my dear friends, you have to be very careful with the rotation. What is the meaning of the rotation? Means rotation and the spin is different. Rotation is different, spin is different. Let's suppose this is one external axis. I will explain about the rotation. Rotational means, let's suppose this is an external axis. This is one external axis. For the external axis, if anything is rotating, then we can say this is a rotation. This we can say the rotation. Now on the external axis, if it is rotating, we cannot say it is rotation. That we can say it as a spin. On its external axis it will spin. Around the external axis it will be rotate. This two is different. Spin is different, rotation is different. Now my dear friends, I will explain general example I will ask you for you. Fan is spinning or rotating? 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 I hope it is clear for you. Fan is spinning or rotating? Now what I said, rotation means any external axis, let's suppose this is external axis. For the external axis, if it is rotating around the external axis, it will be rotate. Now if the axis on the external axis, it will be spin. So yes, what I said, fan is spinning, fan is not rotating, fan is spinning. Why? Because you know this is the external axis. Now this is a bearing, right? Now this is a bearing. Now for this bearing, what it is there? This is the external axis. For this external axis, bearing is there. For this bearing, fan is spinning, not rotating. Now this is the external axis. For this external axis, this bearing is there. Now this bearing is attached to the rotational axis, right? Sir, this external axis. This external axis, fan is spinning, not rotating. Now sun is rotating around the sun. Now this is the sun. Earth is rotating around the sun or spinning around the sun. Now say me, this is sun and this is our earth. Earth is rotating around the sun or spinning around the sun. So if any species, if it is rotating around the external axis, that we say it as a rotation. On the external axis, species will be, or molecule will be spin. On external axis it will be spin. Around the external axis it will be rotate. Okay na? I hope it is clear, difference between the rotation and the spin. Difference between the rotation and spin, it is clear. Difference between the rotation and the spin is clear. For any external axis, species will rotate. On the axis, it will be spin. I hope it is clear. On the axis, it is spinning. Its external axis, it is rotating. I hope it is clear between the spin and rotation. I hope it is clear between the spin and rotation. Now, for the monoatomic gas, if I was taking this as a one external axis for this one, now on this external axis it will be spin. It is spin. But here we are not talking about the, which one? We are not talking about the spin energy. We are talking about the rotational energy, right? On its same axis it will be spin. It will not rotate. So that's the reason entire for the monoatomic gases rotational energy is 0. Translational energy is 3. Then monoatomic gas CV will get, how much you will get? CV is equal to 3 by 2 R. Then Cp will become 3 by 2 R plus R. Then Cp will become 5 by 2 R, right? Then gamma will become, gamma is equal to Cp by Cv, 5 by 2 R and 3 by 2 R. R get cancelled, 2 get cancelled. Then how much you will get? 5 by, for the monoatomic gas, the Poisson's ratio value will get it as 1.66. 1.66. Done? Right. Next. Now we'll go for the diatomic gas. Diatomic gas. For the diatomic gas, if you calculate, E is equal to 3 plus 2. Why? Translational 3, rotational 2. Why? Let's suppose this is the axis. Now the diatomic gas, on its own axis it will be spin, but if I rotate like this, it will touching the x-axis, and here it will be the z-axis, right? It is touching the x-axis as well as z-axis. So around the x-axis and the z-axis it is rotating. On the y-axis it is spinning. So rotational degree of freedom, it is 2. So E is equal to 5. CV is equal to 5 by 2R. Cp is equal to 7 by 2R. Gamma is equal to 7 by 5. It will be 1.4. Right? Next, triatomic gas. Triatomic gas. Now the triatomic gas E is equal to 3 plus 3. Total Cv is equal to 6 by 2R, means is equal to 3R. Cp is equal to how much? Cp is equal to 4R. Now gamma is equal to 4 by 3R. 4 by 3R is nothing but 1.33. Now these are the gamma values for the triatomic gas, gamma value for the diatomic gas, and the gamma value for the monoatomic gas. This will play very crucial role in the upcoming concept that we are going to study. Okay, my dear friends, by this I will stop the lecture because it is already 9, so I cannot provide I cannot extend the lecture. Tomorrow we'll see the work done in the reversible, irreversible, and we'll do the n number of questions, and followed by if the time permits, we'll go to the second law of thermodynamics also. Okay, now by this I was ending the lecture, and see you tomorrow. Any doubts you are having, my dear friends? Any doubts you are having? If you are having any doubts, you can ask me. If you are having any doubts, you can ask me. Any doubts? Or should I end the live? Should I end the live? Okay, fine. Okay, fine. See you tomorrow.